Just as a way of introduction, my name is Gary Johnston. I'm the chairman of the Scottish Local Centre for RMetS, and I would encourage you to join our meeting, join RMetS if you have an interest in meteorology and you're not a member already. We are always looking for new members, and we're happy to see anyone with an interest in meteorology to come along and join us. We can be contacted if you have any comments or you would like further information about this, the Scottish Centre, and then we can be contacted at scotland@rmets.org. Right, our talk tonight, and could I just say before I introduce our speaker tonight that if you have an issue with the quality of sound, we recommend that you use a Chrome browser, and if you're suffering at all to hear anything, then you maybe want to just restart the browser again and log in again. Just also to let you know, all our talks are recorded and are available with the permission of the speaker on YouTube just within a few days of our meetings. Could I also ask that if you have any questions that you put them up on the whiteboard. You'll see there's already comments coming up on the right hand side of your screen, and we will take these questions and read them out towards the end, and our speaker will be more than happy to answer these questions. If you have specific questions that relate to a slide, then could I ask that you just either note the title or the number of the slide so we can try and refer back to it. So we will have the question answer after our speaker is finished. Now, can I introduce tonight, I'd really welcome Dr. Jenny Turton. Now, Jenny, from the bio that we put out, Jenny's had a change of institutions, and Jenny is the senior advisor for Arctic Frontiers. And now this is a non-profit organization which initiates discussion on Pan-Arctic issues and facilitates conference and networks between policymakers, scientists, businesses, and government in the Arctic. Jenny is now based at Turisma in Norway, and her talk tonight is atmospheric processes and their impact on the 79-degree North Glacier, northeast Greenland. So welcome, Jenny.
Thank you very much for having me. I'm very glad to be here. Yes, thank you for the very kind introduction. The work that I'm going to be talking to you about today, presenting, is some work that I've been doing for the last sort of 4.5 years, but also touching on some stuff from even further back than that. I'd first like to just thank some of my co-authors who are based in Europe and also the United States of America. It's Kyle, Jonathan, Xavier, and Bryce. The work was part of a project called the Greenland Ice Sheet Ocean Interaction Project, and we focused on one particular glacier, the 79-degree North Glacier. And the reason for this I'll explain sort of straight away. So tonight's talk is a mixture of atmospheric science and glaciology, and sort of the interface between these two fields. So hopefully you find that interesting. So the Northeast Greenland ice stream is where we find ourselves mostly for this talk tonight. And as you can see from the larger image, this reaches quite far into the center of the Greenland ice sheet. Now, an ice stream is just an area of much faster flowing ice than the surrounding ice. So this is this color red that you can see in the figure. And they are sort of located around the edge of Greenland, many of them in the west. So if you are aware of lots of research going on in Greenland in the past, much of this research has taken place in the west. But it's now becoming a bit more popular to look at the Northeast Greenland ice stream and the 3 glaciers that feed into it. And this is because it has the ability to raise sea levels by around 1 meter should the whole thing collapse. It's just very unlikely, but it is contributing quite a lot to sea level rise already. And this is because it drains around 12% of the Greenland ice sheet. So quite a large area is sort of funneled into these ice streams and out into the ocean. The three glaciers that make up this ice stream are 79 North, which is the northernmost glacier and the one that I work with the most. Then there's also Zachariah-Istrum, a little bit further south, and then Storströmmen, even further south. Zachariah-Istrum you may have heard of in 2012. It lost quite a lot of its glacier. Lots of the front carved off into the ocean. And so this is what really sparked interest in this region, sort of having a look at what was going on to make that happen. And the satellite image that you can see on the bottom, this is from a Sentinel satellite image. The outline in the yellow is what you can see as the glacier. And this is taken in summer, so you can see the exposed rock where the snow has melted, but you can also see that there is still some sea ice at the edge of the glacier, which is pretty important control of the speed of the ice in this region. You can see some other lines on the figure, and the blue one that you can see sort of connecting this part that's sticking out is the grounding line. So this is where the ice from the Greenland ice sheet starts feeding out into the ocean and floating. So the long, thin part that you can see is around 80 kilometers or 50 miles long and around 20 kilometers or 12 miles wide. This part is fully floating on the ocean. And so this means that it's exposed to both a warming ocean and a warming atmosphere. So ice shelves are particularly sensitive. And this is the largest remaining ice shelf in the Arctic. So it's of particular importance. And the reason why we've started looking at this region is that for a long time, prior to 2000, the year 2000, the ice in this area was particularly stable. It wasn't speeding up, it wasn't melting particularly fast. And so a lot of people's interest was on the west part of Greenland where this was happening. But from around the year 2000, the speed of the ice has started increasing. And what you can see here with these dots on the graph on the top picture, you can see that the velocity of the ice is increasing. And this is particularly important at the grounding line, so this region where the ice is touching the ocean, because this is where it starts to melt into the ocean. And so we have increased speed of the ice and also mass loss. And in this region, we've had around a 3-degree temperature rise already since 1979. So already quicker than the global average. You're also getting increased amount of thinning underneath the glacier because the ocean is also warming. And what that's sort of happening recently to tell us that there are changes happening in this region is that in 2019 and 2020, we had exceptionally warm summers in northeast Greenland. And part of the sort of consequences of that was that we had 2 large calving events. So you can kind of see in the north of this picture here, these 2 large chunks and some smaller icebergs that have calved off. And that total area is roughly twice the size of Manhattan in New York. So it is not an insubstantial amount of ice that is being lost. And you can see this smaller graph that's inserted here. You can see that over time, since around 2000, we've been losing area. This glacier has been decreasing in size, but that has rapidly increased in 2019 and 2020. We're also seeing more changes further inland now. So not only on the part of the glacier that's floating, but also the part that is towards the center of Greenland. And these are what you can see here, these blue patches. These are melt ponds. Supraglacial means surface melt ponds or lakes. And these are starting to form on the glacier and the ice sheet. So these often occur in summer, but now we're even seeing that they are happening outside of the normal melting season. They're also spreading quite far inland. And so this is showing us that there are quite a few changes that are happening at the surface of the glacier. And just looking at that image, this is a true color image. So what you can see is this sort of dark gray and blue zone is actually just areas of slush and exposed ice where the snow is totally melted during the summertime. And another reason why we're really interested in this area is because it's expected to be the fastest growing area of ice loss in the future. And so here we are looking at some outputs from some global climate change models, GCMs. And you can see that the northeast section of Greenland, which I've highlighted with the box, is having up to 6 kilometers cubed volume of melting into the future, whereas some other regions are just 2 or 3 kilometers cubed. So we're really trying to keep an eye on this region because it's going to be very important in the future. So the first thought I had when I was trying to put together the talk is that I wanted to sort of explain a bit more about the surface melting and this melt pond development, because it's quite an important area of change. It's everybody's interested in how much mass is being lost or how much ice is being lost from Greenland. And so I think it's important if we first look at what's going on in this region. So when I talk about melt ponds, the word pond is usually thought of as something quite small, but in the case of the Greenland ice sheet, they're not very small at all. They can be a couple of kilometers diameter. And they form because when the surface snow and ice starts to melt, the water can't always percolate down into the rest of the ice and sort of sits on top like a puddle in your garden. And these sometimes have a drainage network where they can connect to each other, sort of where A is leading into C in this figure here. But they can also sort of drain into each other and have a much larger melt pond then. And this is quite important because the albedo of the ice, so the reflectivity, changes in this case. You get these areas of dark blue, which absorb much more solar radiation than the white, bright areas. But it's quite hard to figure out what's going on in northeast Greenland in this respect, because whilst we can see from satellite images, we don't have a great understanding of what's happening underneath that surface because it is quite a hard region to get to. If you are wanting to go and do some flying around there with the helicopter or a plane, it's quite remote from the nearest station for refuel and for staff. So it's quite hard to know what's going on in this region. When you have a thicker snowpack, so lots of fresh snow throughout the year, then you get fewer melt ponds that are forming because the water doesn't need to sit on the surface on a pond. It can sort of trickle through, percolate into the gaps in the fresh snow. But in years when you've got a thinner snowpack or there's been year upon year of melting, then you get a lot more melt ponds because you have a thick ice surface where the water can't penetrate. And as you might expect, a thinner snowpack and less fresh snow is on the cards for this region in the next few decades. So air temperature, rainfall, and also other climatic conditions can also have a big impact on where these melt ponds happen and how often they're happening. It's not only that it's important that they have a topographic depression where they can drain into, but they also need to be prompted by some atmospheric conditions. So here is one study that I was part of last year where we tried to have a look at how different years affect the melt ponds, just 4 years of data we had, but you can see from the different colours here where these melt ponds happened every year. So if we take a year with very few melt ponds, for instance 2018, where you can see the pink in this figure, there's actually very few melt ponds. They're very low down, they're around 200 to 400 metres above sea level. And you can see in the graph on the right-hand side that the pink bar charts at the bottom, that's the lake area. And so it doesn't get particularly many lakes in this region. And the ones that you can see are in the areas where the slope is relatively flat and at low-lying elevations. And in this year, again, we look at the pink. This is how much cumulative snowfall and total precipitation we've had in this year. And you can see that there are periods with a huge amount of snowfall, especially in sort of March and late May. You get these huge inputs of snowfall into the region, which means that by the time the sun returns in this region and we have a lot of solar radiation, there's a very thick snowpack for this water to penetrate into. Here we have the temperature. The vertical lines that you can see are when the melt pond first opened, and the difference between the straight and the dashed line is just two different regions, not particularly of relevance for this talk, but what you can see, especially with the dashed line, is that you've got quite a lot of cooler than average temperatures in this region. So the grey lines in the background are the average conditions since 2009. And the pink is in 2018, and you can see that in many of these days of the year, the temperature is below average for this region. If we then compare that to 2016, now the blue melt ponds that you can already see from the figure on the left-hand side that these are reaching much higher elevation than the pink year. So 1,400 meters above sea level, even higher than that in some cases. And you can also see the huge amount of lakes that are happening at these higher altitudes compared to the year before. And conversely, in this year, we had a lot less snowfall throughout the year. So more similar to the other 3 years that we looked at. But you can see here as well the difference between the dashed line in July, August time and the straight line. So the dashed line is where we've got rainfall, so liquid precipitation is happening quite a lot in this year instead of snowfall when it comes to the summertime. And with the temperatures, you can see that at the very start of the summer season in June time, there is this big increase in temperatures, this big jump, and then they remain above average for most of the year until around the end of August time. So if we were to look at all 4 years that we looked at in total, you can see how much it varies year by year, where you have 2016 in the blue and 2019 in the purple, which had a lot of melt ponds. 2019 was this warm year where we had the calving event I mentioned. And then conversely, 2018 is the pink, and 2017 in the middle was a bit more of an average year. Then we wanted to have a look about more than just melting, but something called the surface mass balance. And this is the balance between the incoming amount of mass, in this case snowfall, and the outgoing amount of mass, which is melting but also runoff. So once this melt pond has developed, usually the water doesn't just sit there and refreeze, it often drains through either to the ocean or to the bottom of the glacier. And this means that this is being lost from the system. And a negative mass balance is where you've got more mass being lost. So there's more melting, more runoff than there is snowfall coming in. And Greenland in general as a whole island has been losing mass since the mid 1990s, and that is accelerating in the last few years. So when we had a look at the surface mass balance, so we ran here some surface mass and atmospheric models to have a look at what was going on, as well as the melt ponds. And we can see a very similar picture here. So the time frame is slightly shifted. So in the previous figures, we didn't look at 2014. So this A is not really of interest here, but B and C are these warm years that we had in 2016, 2017. And then D, where you've got a lot more of the blue over the region. This was in 2018, where we had very few melt ponds. And this kind of shows us how important these two criteria are together, because especially in 2018, you are actually gaining mass. We have a lot of snowfall happening, which is why it's blue. And the red area where we're losing mass is really only in the very low-lying regions where we had these melt ponds. So we can already say that if we're able to look at these melt ponds, and that's the only information we had for the region, if we didn't have any atmospheric models or any observations of the weather, maybe we can already tell what was going on in this region in terms of the weather characteristics. And this region, in some cases, is indicative of the whole of Greenland. So in 2016, here we can see the whole of Greenland. And in the top right, this red dot here by KPC, this is Northeast Greenland, where we were looking. And you can see that the whole of Greenland in 2016 was losing mass. So it was a very warm year for the whole of Greenland. Whereas if you look in 2018, there's a bit more of a north-south divide. So in the north, you've got very cooler conditions and you're getting a lot of snowfall. But in the south, you're still having quite a lot of melting. So why is it that in some years you're having the whole of Greenland experiencing something, and in other years it's very different? And we wanted to have a look at what specifically about the weather conditions or the atmospheric processes were causing this change of conditions in the northeast. And so the question was posed as which atmospheric processes are important? What is it exactly about the weather conditions in this region that's making it melt much quicker than in other places, and especially since the 2000s? And there are many different ones, but we, at least in this presentation, focus on atmospheric rivers and föhn winds. And I will now go on to talk about what those are and how they contribute to the melting. So atmospheric rivers, they've become quite a hot topic, let's say, in research recently. They've got a cool name. They're kind of, you can imagine them quite easily because they really are like rivers of the sky. They're narrow conduit or filamental type features with high water vapor transport. So in this figure here, where Greenland is in the center of the globe and it has a black outline, you can see that on the western side of it, you have this region outlined in purple with really high amounts of water vapor transport. And this is an atmospheric river. You can also see them in different regions across the globe here. They don't only happen in Greenland. But what they do is bring a lot of moisture and a lot of warm air from the tropical regions into the poles. They're one of the most important transports of this warmth and moisture into the Arctic. And often they go along the west coast of Greenland. because they are often associated with a storm, a low pressure system, or a hurricane. So in the summertime, when you get this development of hurricanes across the east coast of America and in the Atlantic, these then come up the west coast of Greenland and are an atmospheric river by the time they get to higher latitudes. Now, there's been some studies done by my colleague Kyle, who was looking mostly at the west coast of Greenland. If they're happening in this region, they must be having an impact in the west coast. And of course, they are. They bring a lot of moisture and therefore a lot of snowfall in the west coast of Greenland. And so you can see on the left-hand side, this is what the climatology looks like in June, July, and August, with the mean surface mass balance. So blue, where we've got more snowfall, the melting. And then you can see on the right the difference then when you're looking at these atmospheric rivers, and you can see a lot more mass gain in this region, this blue area where there's more snowfall, even though they only occur around 5% of the time. So then we wanted to have a look, well, what's happening on the east coast, the northeast coast? Is anything happening when they're hitting here? Because that's quite a long way away from the northeast to the west coast. And what we found is that when these atmospheric rivers are coming up the west coast of Greenland, they do actually have an impact over 1,000 kilometers away on the glacier that we're looking at. So on the left side here, you can see that there's this cloud, not a real one, just something to point out what I mean here. This is where an atmospheric river might make landfall. So where it comes from, going along the ocean, and it hits the west coast of Greenland, and it deposits all of this snowfall, which is why we've got this dark blue region of snowfall here. And what you can start to see on the other side of Greenland is sort of a reddish, not the super strong, but a red mass loss. So here we're having some melting that's happening. And especially when this atmospheric river goes a bit further north and sort of goes between the northern eastern part of Canada and Greenland, you can see that the area of our interest, the northeast, is much more red here. So there is much more melting that's happening. And this wasn't just for one atmospheric river that we found, but this was for many. So we thought, well, let's take a look a bit deeper into what's going on in the northeast when these atmospheric rivers are hitting 1,000 kilometers away. And the hypothesis that we came up with was a process called föhn winds. Now, föhn is a German word. It nowadays translates to hairdryer. And the reason for that is because these winds are very warm, very dry, and they blow downslope. And they're caused by the interaction of the airflow in a mountain range. So when an air mass comes across an obstacle, a mountain in this case, the air is forced to rise at the dry adiabatic lapse rate, and it condenses, and often there is rainfall or snowfall that happens with this. And then as the air mass then continues to rise further, it rises at the saturated adiabatic lapse rate, which is a cooler rising rate. Then when it overcomes the obstacle and it descends down the other coast, coast, I suppose, in this case, but the other side of the mountain, it descends at the warmer dry adiabatic lapse rate. And so then you get an offset in the temperature where it is much warmer upstream than at the same elevation downstream. And so this happens a lot in the Alps. This is where they are most famous for, and they're most well studied. But they also happen in many other cases, including over Scotland. So often when Scotland has particularly warm winter days, so in this case in 2020 it was 18 degrees. I think over Christmas this year and New Year it was also particularly warm, and often that's because of föhn winds. So the air mass is coming across the Atlantic, hitting the mountains of Scotland, and when it reaches the other side, it's starting to descend and it heats up. And this also happens in the Antarctic, South America, North America, New Zealand, in many places where you've got a mountain range or a single mountain sometimes, and some strong winds. And in Greenland, it's a little bit different because we don't have a very stark, strong mountain range that sticks up. It's more of a gradual slope. It's a little bit different, but it's the same process that is happening. And so what happens at this figure on the top here is when we do not have any atmospheric rivers, the green is moisture. So the darker the green or the blue, you've got really saturated conditions. And on the east coast, where this brown like sort of section is on the topography, you can see that it's quite moist still, and there isn't any drying happening. However, when you get an atmospheric river, which hits the west coast. Again, similar before, you get a lot of moisture deposited here. But then if you look onto the east coast, you can see that it's much drier, less than 50% relative humidity, all the way down to the low-lying regions. And so looking into this previous work that had been done, we thought that there was something here that our hypothesis was probably correct. So we decided to have a look at a case study. We just took one particular strong atmospheric river that was detected on July 18th and 19th in 2014. And in this synoptic figure here, you can see it's sort of associated with a low pressure system that's coming across Canada. And on the right-hand side, you can see these arrows here and the colours of the wind speed. So it's picking up speed and it's traversing across the ice sheet from west to east. And around 2 days later, it actually increased in both speed and moisture. And so now we had what we're calling a strong atmospheric river. So one that's higher than the 90th percentile of moisture in this region. And here you can see much stronger winds, and also this red outline that you can faintly see is areas of melting that is happening because of this atmospheric river. We developed an algorithm to have a look at these föhn winds. So we wanted to know where on the ice sheet is it particularly dry, much drier than average, much drier than even extreme conditions. It's warmer than it was before, and where the wind is coming from across the ice sheet and also is quite strong. And from that, we can see during this case study that before the atmospheric river makes landfall, the wind in this region in the northeast is not particularly strong. It's from different directions over the ocean. It's coming from the Atlantic, whereas in other regions it's southerly flow to the south flowing. However, when our atmospheric river starts to make landfall on the west, you can see that automatically this wind is starting to become downslope, starting to go across the ice sheet. And you get this big area in red here is where we've identified a föhn wind in this case. And the background colour that you can see is the hourly melting, this sort of purpley reddy colour. And you can see how much higher up the ice sheet that it's going, this orange area, very similar to the location where we had all of these melt ponds at the start of the presentation. Oops, sorry, that was my email if you just heard that noise. And then we wanted to have a look at what this looks like vertically. So we ran a simulation with a high resolution model, 1 kilometre by 1 kilometre resolution. And we could see a similar thing, that before the atmospheric river, we had very clearly stratified air over the glacier. This vertical line here is roughly the middle of the glacier. And it was not particularly warm. However, as time progressed through, this föhn wind starts to develop. We have a lot of downslope flow, a lot of mixing of conditions from aloft, and it's very warm over the ice sheet, around 8 degrees, which is way warmer than average in this region. So we now know that, at least on a case study by case study basis, we could see this was happening, and we were pretty confident that the reason for these föhn winds developing was because of these atmospheric rivers. So then we decided to look over a longer period of time, and we have data from 1980 to present now from a number of atmospheric models that can tell us what the conditions were like over the last 30 to 40 years. And here on these figures, there are 2 different lines that are going on, a dashed and a solid. There isn't too much to worry about the solid one. This is just, we did a few different methods to make sure we were really confident with our results. But the dashed line is how many of these atmospheric rivers you're seeing per year. And so this varies quite a lot to sort of 12 to 13% of the time you're getting these atmospheric rivers. But in some cases, especially in the last few years, there's been much higher variability. And there's also an increasing trend. So these atmospheric rivers are increasing more, are happening more often, and they are happening more, especially when you're looking at the extreme versions, the ones that create the biggest amount of melting. These are increasing quite a lot. So even though they were naturally happening, something seemed to have changed, especially from the year 2000, that we're having a lot more of these atmospheric rivers happening every year now. And because we're interested in the ones that are stronger, so if the strongest atmospheric rivers are happening more often, what does that mean for our region in the northeast? We had a look over this whole time period for every case when there was an atmospheric river. We broke it down into how strong it was. And so these bar charts you can see here are increasing from around 100 kilograms per meter second of moisture all the way up to around 750 was one of the strongest. And how much melting that is producing in this area in the green box, which is the northeast. And we can see that when these atmospheric rivers are stronger, there's more moisture. And with climate change, there is a very high probability of having more moisture in the atmosphere, especially in this region where we've got a lot of sea ice that's melting. We're going to have potentially more very strong atmospheric rivers going into the future. And these are causing more melting in the northeast of Greenland, our area of interest. When we are back now just looking at the northeast and we're trying to say, okay, so we know that they're strong, we know they're increasing, but they still don't happen that often. So how much melting can they really create if they're only happening a few days a year? Well, in fact, over 50% of the summer melting in this region of the northeast can actually be attributed to this condition that we're looking at, this atmospheric river föhn wind interaction. So around 50%, around half of this is happening. Then if we look at these extreme conditions, we find that around 75 to 100% of this extreme melting is happening because of this condition. So in almost every case where in the northeast of Greenland, you're having extreme melting conditions, a lot of melting over a couple of days, the reason for this can be attributed to these atmospheric river föhn interactions. And so in this figure, it's these dark patches here. You can probably see the outline of the 3 glaciers that I mentioned earlier, 79 North, Zachariah and Storströmmen. And you can also see the elevation that this melting is happening up to. So around 1,500 meters above sea level or to 2,000 meters, which is again this region where we're starting to see more and more melt ponds forming. So we think that there is a sort of a direct tie between the atmospheric rivers, the föhn winds, and then the melt ponds as a sort of knock-on effect, a domino effect that is happening when these atmospheric rivers are hitting Greenland. So over time, the amount of melting that's associated with these has been increasing. So here, this figure isn't just melting all the time, because we know that that has already increased, but actually melting that we can specifically pinpoint to these atmospheric river föhn events. And so from the year 2000, especially, you see this big jump here, that between sort of 0 and 1,000 meters above sea level, we're having a lot more melting that's happening because of these. And this is also the case at more than 1,500 meters above sea level, where there is very little melting normally. But during these very intense periods, we are seeing some melting now. And this has also been looked at in a few other models. Here I've just shown one, but in fact we double checked with a few models to make sure that there wasn't just something happening in the data that didn't give us confidence, but we're actually very confident that this process is happening. And so if you remember back at the start when I sort of showed you the graph of when the ice had been speeding up and when this area became kind of interesting to study, it was around the year 2000. And so in the year 2000, we've had this sort of switch from atmospheric rivers that are happening sort of 12% of the time to huge changes year on year on how many are happening. It's becoming quite volatile in terms of the weather conditions, but we're having more and more of these atmospheric rivers. So just to summarize the sort of this presentation that I've given here, we attribute the melting in this region, especially the extreme melting, to these föhn winds, these warm, dry, downslope winds. And these are directly triggered by this atmospheric river that crosses from northwest to northeast of the ice sheet. One question I often get asked is how we can tell the difference between the föhn winds and the Katabatic winds. And one of those reasons is because the Katabatic winds happen quite regularly, especially during winter time, but there isn't any of this melting associated with that or any sort of jump in temperature. These föhn winds are creating quite warm conditions very quickly, where the ice can start to melt quite quick, and then that continues. And approximately 75 to 100% of the extreme melting events, so these are where you're getting 99th percentile, very extreme melt days. These are attributed often to atmospheric river and föhn relationships. And there is now some evidence that this has been increasing over time since around the year 2000. So this is definitely something that we need to look at in the future, keep our eye on, because as the models are telling us for the future, it's only going to get warmer and it's going to get more moisture in the atmosphere. And so whilst we haven't yet done the study for this, it's going to be interesting to see how many atmospheric rivers we're predicting to happen into the future. So I'll just leave here with some of the references that I've used throughout the talk, but thank you very much for your attention. I'm really pleased to give the talk here today, and if you have any questions, I'd be really happy to answer them. Thank you.
Yeah, thanks very much, Jenny. It was very interesting. I managed to find a camera sorry about the quality. It's an old one I managed to plug in just as you were speaking there. But no, that was very interesting. And we have a few questions. The first question from Veli, who is from the Sea Research Society. What do you think about melting after the Arctic Ocean becomes sea ice free? Do you think it will make less or more atmospheric rivers over North Greenland ice dome?
That's a very good question. I think the location of the atmospheric rivers is going to be interesting here. So the Arctic Ocean is losing ice, especially of this northern Canadian region and northern Greenland region. And so whilst it's not very common, there are sometimes atmospheric rivers that come sort of from the pole down towards Greenland. And it is potentially likely that those will increase in, in frequency because you'll have a lot more moisture available when there's less sea ice. In the region in Baffin Bay, which is this west coast of Greenland, there isn't that much sea ice always anyway there. So I'm not sure that would change too much. And because the ones that come up the west coast are often associated with lower mid-latitude conditions, sort of hurricanes and extratropical storms, perhaps they're not so related to the sea ice. But I think once it becomes sea ice free, maybe we'll be having moisture transport from regions that we don't see so much currently, sort of from the Arctic Ocean down towards Greenland. Recently we had, I think last summer, the summit of Greenland, so where there is very little melting and usually very little precipitation of any kind. We had a lot of rainfall, and that was associated with an atmospheric river for the first time. So maybe that's a sign of things to come.
Okay, thank you, Jenny. That's maybe one, Veli, you want to follow up on. A question from Anthony. What height, thickness are the atmospheric rivers on approach from the west?
So we had a look at an integrated column water vapor transport. So we took all of the moisture from 1,000 hectopascals to 200 hectopascals. We didn't look specifically at how thick they were, but the vast majority usually is a sort of around 800, 900 hectopascals. Because the clouds that are associated with this are usually quite thick, low-lying clouds, and they also contribute to melting through just long-wave radiation. So we didn't look specifically at how high or how thick, but we took all of the moisture between 1,000 and 200 hectopascals.
Okay, thank you. A question from Rex. Does the föhn include melting affect the salinity near the Greenland coast? And have you found any important implications?
Yeah, so the project that I mentioned at the start, the Greenland Ice Sheet Ocean Project, GROSS it's called, was mostly involved with ocean scientists. So I was actually the only atmospheric scientist on the project, and everybody else was oceanographers, or most people were oceanographers. And they are looking specifically at the salinity underneath and around 79 North. And they've also found that there's been a change in the salinity, that there has been more basal melting from the underside of the ice sheet, around 10 meters a year. So it's quite a big amount of mass that's lost compared to the thinning on the surface, which is around 1 to 2 meters. But it does, yeah. So I cannot say exactly the föhn induced specifically, because the way that they look at the salinity is more of a seasonal or yearly cycle rather than a day-to-day event like the föhn. But if the föhn is increasing the melting, I can imagine that that increase in salinity is partially to do with that.
Okay, thank you. A question from Dom. Are there any areas where there is a net accumulation?
Yeah, so I mean, on an annual cycle or an annual scale, around 1,500 meters and above, you do have a net accumulation. You have more snowfall than the melting, or generally there's very little melting. And generally everywhere below that is where you have an ablation zone, where there is more melting. When we're looking at these specific föhn atmospheric river events, if that's what this question's about, on the west coast, you do have a net accumulation with these because there is a lot of snowfall that happens as the air mass is rising up the west coast. There's a lot of precipitation, a lot of snowfall, and it's really only when it gets to the east side of Greenland that it starts to descend. So there is a big accumulation on the west coast and a large amount of melting on the east. And I think it should be looked at as a whole system so that we can try and figure out whether the melting offsets the accumulation or which one is kind of winning, shall we say. That we didn't do that in the study, but I think it is an important area we need to look into.
Okay, thank you. A question from Miriam. Where did you get your wind velocity data from?
So there are 2 weather stations in this region that are operated by the PROMICE network, which is part of the Danish and Greenland Geological Survey. And it's called Kronprinsland Lower and Upper. So there are 2 stations. For the sort of 2D figures that I showed of the maps, it was from an atmospheric model. So we used a few different ones, the Weather Research Forecast model, the RACMO model, and the MAR model. These 3 have been used, but if you want observations, I'd suggest looking for PROMICE. If you just do a Google of PROMICE, they should come up.
Thank you. Right, questions are coming in, really interesting. One from David, who is interested in what happened to your surface melt. Can it stay on the surface surface to freeze in winter, or is it lost in the subglacial drainage system?
Good question. And a part of that answer, I don't know, because it's ongoing, this research, but some of it does drain. So as well as the melt ponds filling in, you can have a look at the satellite data, because it happens every day. The image is taken every day, that suddenly the melt pond has disappeared, or it looks empty, and it happens in less than 24 hours. And the only explanation for that would be that it's drained somewhere. So in other parts of Greenland, you can see these huge waterfalls happening where this all of a sudden this lake just disappears. It's drained out through sort of a drain pipe almost, and it's disappeared in a few days. We do see that on a few of our melt ponds, but not all of them. The ones that are lower down, they tend to refreeze in the winter. And the problem with that is that the surface is then preconditioned so that next summer it's a lot easier to melt, and there's a lot easier for a melt pond to form. So in those figures that I showed, where you could see that melt ponds in the different colours year by year, some of them had other colours as well. So especially in 2016, 2019, the same melt pond filled again and again. And so in that case, it's probably because they refreezed and refroze, and they were able to melt again. But many of them are draining. But we want to know how many, so that we can start seeing how much of this volume of water is contributing to sea level rise. And that's sort of ongoing with the project now.
Great, thank you. A question from Anthony. What is required to adequately predict ARs, and were their effects assessed or factored into the IPCC special report on ocean and cryosphere?
Oof, wow, difficult and great questions. The second part, I'm not too sure about. The IPCC. I don't know. I mean, a lot of studies on surface mass balance were included. A lot of studies on melting were included, and so even if they weren't directly included in the IPCC, indirectly, their effects probably were. In order to predict them, we need slightly higher resolution models than the current global climate models. Some of them are high resolution, but the data we were using was around 15 and 5 kilometer resolution, so really high resolution, whereas the global climate models at the moment are 80 to 100 kilometers. So you can see some of these atmospheric rivers because they are quite large effects, phenomenon, but you need sort of higher resolution models, and you need to know about the general circulation that's happening in the region, because they're often associated with extratropical storms and hurricanes. So if those are adequately predicted, sometimes you can predict an atmospheric river from those. However, I mean, as we all probably know, day-to-day weather is hard to predict, let alone, in the future. So I think that there's still an area of research that needs to be done here. As I'm aware, there aren't any studies yet saying what we're expecting of atmospheric rivers in the next 100 years, but it would definitely be interesting to find out.
Thank you. There was just a comment came in there from Veli from the Sea Research Society. And basically, I've seen satellite images of frozen melt water ponds that freeze in winter in the area. So it's more a comment.
Mm-hmm. Yeah.
Thank you. And Miriam again, did you look at how the Föhn winds impact East Greenland ice in any other way or only melt by increased temperatures?
Yeah, as a first look, we've only looked at the increased temperatures and the melt. This work took quite a long time actually to get off the ground, because there hadn't really been many other fern studies in this region, apart from a couple of case studies. But in terms of trying to develop a way to really observe the fern and make sure that we were picking up the right signal and it wasn't something else that was happening in the region, it took quite a long time. And so as a first step, really, we've only currently looked at the melting and the increased temperature, but nothing else so far.
Thank you, and thank you coming in from, I think, in fact, everyone's asked questions. They said, great, thanks very much. So some great answers there, some good questions, actually, some great questions, and thank you for answering them. I don't think we have any more questions, but yeah, really fascinating talk and fascinating research, Jenny. So and thank you very much. Oh, Jonathan, there was one came in from Jonathan, but I seem to have lost it. Sorry, bear with me. Do the AR correlate with hurricane intensity and number?
Yes, I'm not sure exactly how well they correlate, but at least these very extreme situations we had where there's been a lot of melting at high levels, especially at the summit station, these are always associated with a hurricane, and usually a quite intense hurricane. So Hurricane Sandy from, when was that now? 6-7 years ago, maybe even longer. That had quite a few atmospheric river situations associated with it over the sort of southern part of Greenland. There was a lot of rainfall happening then, and that was associated with the hurricane. I don't know, at least in Greenland, of how many of these atmospheric rivers are directly related to the hurricane. I couldn't say, but yes, the ones that hit the west coast of Greenland are definitely associated with the hurricane, especially strong hurricanes.
Thank you. And another late question just coming in from Anthony again. Are there synergies between ARs and the jet stream? Interesting question.
Ooh, that is an interesting question. I would say definitely the location of the atmospheric rivers will be related by the jet stream, because again, the jet stream is also responsible for the low pressure systems that we get, and many of these atmospheric rivers are the sort of tail end of the low pressure system. So I would say in terms of location, yes, but anything else, I'm not sure. That's a good question, and one that I would like to know the answer to myself. So maybe I'll be spending the next half an hour doing some research.
Yeah, good point, Anthony. I think there needs to be more research on that one. So your comment there. Okay, Jenny, well, thank you again very much for coming along and giving this excellent talk tonight. And I think we've had probably more questions tonight than we've had for most of our speakers, and we're very grateful for your time. And a lot of thank yous coming in. Just before, if you could maybe hang on so we can thank you properly on behalf of the Scottish Centre. Could I just say to the public that normally at this stage we would be congratulating and saying thank you very much. So I'm sure there's a number of claps coming in and thank yous. So we very much appreciate that. And it was nice to see so many people attending tonight and joining in. And as I said, this talk, like all the others, will be available on YouTube within the next few days, subject to Jenny's approval. Could I just take this opportunity to formally thank Dr. Jenny Turton on behalf of the Scottish Centre, and thank you all again for coming along. I would also like to give special thanks to the people behind the scenes. As you've seen, we had I personally had a bit of a hiccup tonight, but there's a few people behind the scenes to make this all work. So thank you to Alan MacDonald and Richard Tabinet, who are there and making sure things are happening. Could I also remind you all that our next meeting is on the 18th of February, and it's our postgraduate showcase. So that should be a very interesting event as well. So again, thank you all for attending, and thank you, and hope you have a very good new year going forward. And I hope we can all get through this COVID situation and back to normal as quick as possible. So thank you.
Thank you, everyone.